All right, let's get started. Okay, your next homework assignment, 4B, is due a week from today. And remember, of course, that we've got lab today and tomorrow afternoon, depending on which one you're assigned. We're going to be continuing talking about Euler's equation today. So any announcement questions before we get started? All right, here's Euler's equation. And what it says is that when we're inside of a fluid, there's a change in the piezometric pressure due to an acceleration in a certain direction, here indicated the L direction. So let's say that we've got 2 points that are a certain distance apart. That's here the delta L. Between those 2 points in the fluid of given density, the piezometric pressure changes. Now, the piezometric pressure is the pressure plus gamma z, where what we're keeping track of is not only just the actual pressure itself, but the elevation of the location relative to a datum. So in our 2 points, we're going to be looking at both their elevation and the pressure. And what this negative sign is indicating is that the pressure change is in the opposite direction of the acceleration. So remember what we said last time was that if we had some sort of a fluid container and it was accelerating to the left, that the pressure increase would be to the right. So this is the version of the Euler's equation that will be on the formula sheet that I give you for the next exam, but you'll never substitute numbers in directly into this equation. I mean, unless you're making a mistake, then you will. But if you're solving the problem correctly, then what you'll do instead is you'll say, well, I'm going to apply this generalized formula in a certain direction. And let's just say maybe that the acceleration was in the x direction. So here, instead of L, now we're saying, let's assume a linear variation in the piezometric pressure and that the acceleration is in the x direction. So the way that we further expand this equation is we say it's between 2 points. This delta x is the distance between the 2 points in the x direction. And so the piezometric pressure at location 2 minus the piezometric pressure at location 1 is equal to the negative of the distance between them in the x direction, the density of the fluid, and the acceleration in that x direction. So this is the version of the Euler's equation that then you would start substituting pressures and distances and acceleration and densities into for problem solving. You could also rewrite that same equation in a different direction. This x was just as an illustration. We could also do it in z if we were interested in what acceleration was happening in the vertical direction. Now here, 1 and 2 are indicating 2 points. And it's very important that you understand the convention that's built into the equation here on what we mean by 2 and what we mean by 1. Specifically, if we're acting in some certain direction L, then 2 is the location with the most L, the most direction. So in the case of x, it would be furthest to the right. So here's a coordinate system that's showing if x is the horizontal direction, then location 2 would be whichever of the 2 points of interest in the x direction is furthest to the right, and you'd assign location 1 to the point that is further to the left. And if we were working vertically, then 2 would be whatever's higher than location 1. And we'll get some practice assigning that, but unfortunately, if you mix it up, if you get 2 and 1 accidentally switched, then you'll get an error in applying Euler's equation. The other thing that goes along with that is that acceleration has direction associated with it. And so here, acceleration in the x direction, positive would be to the right, and negative would be to the left. And so in addition to keeping track of what is 2 and what is 1, then you also need to know the directionality of the acceleration. So I'm sure you have lots of questions, and this doesn't become immediately obvious of how to apply until we start plugging in some numbers here. So let's just say, for sake of illustration, that we have a tanker truck that's carrying gasoline, and we've got the dimensions of the truck. It's 6.1 meters long, 1.83 meters tall, and we've got a couple of different locations of interest here. Location T is at the top left. Location A is over here at the top right, and then location B is on the right side but at the bottom. And it's known that the pressure at location T is equal to 0. Maybe that means it's open to the atmosphere, although since this is a tank of gasoline, hopefully not, right? Be a little dangerous. All right, so this truck is carrying gasoline, and we know the fluid properties of the gasoline. Here the unit weight is 6.60 kilonewtons per cubic meter. So if we're given the unit weight, then we can get the density, which we will need for Euler's equation. And then it's slowing down at a rate of 3.05 meters per second squared. So it looks like the truck is moving to the right, and it's slowing down. So what does that tell us about the acceleration? Negative. Exactly. So the direction of the acceleration is to the left, and so when we expand out Euler's equation, we're going to need to make sure that the A that we put here is going to be a negative value. Okay, so what I'm going to have you do is solve this in two different segments. In the first segment, we want to know what's the pressure at point A. And so Euler's equation for doing that is going to be P plus gamma z at location 2 minus P plus gamma z at location 1 is equal to the negative delta x density times acceleration in x. All right. So what was the rule in terms of what's location 2 and what's location 1? Do you remember what I said the standard notation or the standard approaches for that? The rightmost is what we call location 2. And so we're in the x direction for this first problem, where it says the pressure in point A, we're working in the x direction because that's the acceleration is in the x direction. And so what should I say is 2, man, this is a crappy marker, I just barely got it. Luckily, I also brought a backup. Okay, so 2 is what and 1 is what in terms of the letters A versus T? Okay, that's right. 2 is A and 1 is T. And so now, if I make some substitutions here into Euler's equation, what that means is that the pressure at A plus gamma z A minus the pressure at T minus the gamma z T is equal to negative delta x between the 2 points, the density of the fluid, and the acceleration in x. All right. So with that expanded version of the Euler's equation, do step 1. What is the pressure at point A? We know everything in there except for pressure of A. Solve for that. And then once you feel confident that you've got that, of course, check with your classmates, make sure everybody's on the same page. Then think about part 2 here. It's asking where in the tank is the pressure the highest? Anywhere in the tank, where is it going to be the greatest pressure, and try and solve for the pressure at that point. And we will get back together in a few minutes and go over the solution for that. Okay, so I've got the answer to part 1 up on the screen right now. And maybe I didn't specifically mention it here, but Z is talking about the elevation above some datum. And so in the case of our truck, it could be that the datum is the bottom of the truck, or it could be that the datum is the top. But as long as we're measuring the elevation at both points relative to the same datum, then it ultimately doesn't matter, especially because here that the elevation of A and the elevation of T are the same. So you'll notice that when we start doing the substitutions here, I rearranged to isolate PA. And so it's the pressure at T minus the changes in pressure that are due to some distance, an acceleration, and a density. And so in a way, if you think about it, this distance, density, and acceleration, that's very similar to the hydrostatic equation, right? Because the hydrostatic equation was delta H times gamma. So here all we're saying is the acceleration isn't gravitational, it's some horizontal acceleration, but we still have a distance between 2 points that the pressure change is accumulating over. So it's an initial pressure and then some change. And so here the pressure at A should be 12,517 pascals. Okay. Any questions about that first part? The key things that I'll reiterate is how important it is to get the right location 2 versus the correct location 1, and then also interpreting the sign of the acceleration. And it's implied that this truck was driving to the right, but I suppose it could have been driving, maybe it was backing up and it's slowing down as it's backing up, but that's not what it was. All right, so where is the pressure the greatest? So here's what we can do. We can apply Euler's equation between any 2 points. As long as the acceleration is just in one direction, then we can apply it between any 2 points directly. So we know now the pressure at T and the pressure at A. So we could apply Euler's equation from T towards B or from A to B. And we'll get the right answer either way. What I'd suggest you do, just to get a feel for how Euler's equation already takes into account the hydrostatic equation, is apply Euler's equation between T and B. And now the trick there is, sometimes people get hung up on, is picking out what is location 1 and what is location 2. So this truck, remember, is accelerating in the x direction. So between T and B, what's location 2 and what's location 1? 2 is B and 1 is T. And the reason why sometimes that fools people is that T is above it, right? So if you were thinking in the vertical direction, then T would be location 2. But here, our acceleration is horizontal. So it's whatever's furthest to the right gets assigned number 2. B is to the further to the right. So apply the same Euler's equation that we did before, where we're saying it's the pressure plus gamma z at location 2 minus the pressure plus gamma z at location 1 is equal to the negative delta x density acceleration in x. And we want to know pressure at B. Pressure at B is what? And that's where the pressure is going to be the greatest, because if you think about it, we just found that the pressure at A was 12,517, and then B is going to be even more because it's underneath it. So pressure is going to accumulate as you go down through the fluid. But Euler's equation will allow us to go from T to B, and it'll take the acceleration effect into account and also the vertical hydrostatic-like effect into account in the same single calculation. So how many people got 24,595 pascals? Good, good. All right. So I like to break it up into parts and think about, all right, some of the pressure was due to the acceleration in the horizontal direction, and some of the pressure was because of the elevation difference between the two. And so that 24,595 looks like 12,000 of it was because of the elevation difference. So that's where we have the unit weight multiplied by some elevation difference. 1.83 was the elevation difference, right? And then the second component was minus, but then our acceleration is negative, so it's going to be a combined increase in pressure due to the horizontal acceleration. So 24,595. And what that shows us is that Euler's equation simultaneously, if you're going, you have both a change in horizontal position and vertical location, it takes care of the pressure change of both effects, the horizontal acceleration and the gravitational effect. And so you don't need to double account for that gravitational effect. One of the common mistakes that students make, besides 2 versus 1 definition, and besides forgetting the negative sign for acceleration, I'd say maybe the third most common mistake when Euler's equation is that sometimes they'll do Euler's equation and then they'll also add on to it the hydrostatic effect. But you don't need to, because Euler's equation already has that covered. All right. Easy enough, right? Let's look at another example. Any questions before we move on? So this pressure change was because of acceleration. And that's mainly what we're talking about today, is how the local acceleration is changing the pressure of a fluid. Local acceleration can also change the location of a fluid. And that's why Euler's equation keeps track of pressure plus gamma z. Because this tank was enclosed at the top, had a lid on it. If there was no lid, then the liquid level would be sloshing back and forth. And so Euler's equation can also predict how the liquid elevations would change if it's in an unconfined tank that's open to the atmosphere. We'll do that a bit later. But for now, let's continue to assume that we have an enclosed container. So Euler's equation can be used to describe a fluid accelerating through a pipe due to a velocity increase over time. So let's say that water's flowing through a pipe, and we want to know what pressure gradient is required to accelerate water at a rate of 6 meters per second squared. So pressure gradient, what that means is a change in pressure over some distance. So if we just arbitrarily picked a couple of points and we said, well, let's assume that these 2 points are 1 meter apart. What we want to know is how much higher does the pressure at A have to be compared to the pressure at B in order for the water to be accelerating in the right direction at 6 meters per second squared. And the fluid would be accelerating to the right if we had extra pressure at A compared to B. And so you can use Euler's equation to solve for that in the same way that we did in the previous example. It's just that now, instead of the acceleration, I guess acceleration is given again, we're trying to find the change in pressure. So it's not necessarily an absolute pressure at a certain location, but it's delta P. So in other words, we're saying the pressure at B minus the pressure at A. And here you can see in this example that the pipe is horizontally oriented. So it's a horizontal pipe, which means that ZB and ZA are going to be the same. So, all right, let me give you a few moments to work on this and try and find out the pressure gradient. So that the answer of a pressure gradient should be pascals per meter. Okay, so who got negative 6,000 pascals per meter? Why is it negative? What does that mean? Losing pressure from A to B. Right, so the fluid is moving from A to B, the pressure is decreasing, and that makes sense. You know, water flows from locations of high energy towards low energy. And that's why water flows downhill, is it's going from high potential energy towards low potential energy. And in an enclosed environment, in a closed conduit like a pipe, water flows from high pressure towards low pressure. So in other words, this is saying that the acceleration is to the right, the pressure increase is in the opposite direction of the fluid acceleration. So if it's accelerating to the right, then the pressure increases to the left from B towards A. So that's why we ended up with this negative value in the calculations. All right, and looking at the units tells us if we have a kilogram meter per second squared, that's a Newton. And newtons per meter cubed is the same as pascals per meter. Yeah?
Is this considered like a large value or more of an average?
Good question. So we're talking about 6 kilopascals per meter. That's a lot of energy loss. That's a big pressure. Yeah, that's a lot. So it's maybe a pretty extreme example. Other questions about this one? All right, you're getting good practice substituting values into Euler's equation. Several years ago, on the midterm, students were just really struggling with Euler's, and so I threw in a lot more examples than I had before. So I hope that this makes it a lot easier. Now, this is taking it to the next level of difficulty, and now the issue is that we have acceleration in two directions at the same time. So if we just look at what's going on here, we've got an enclosed tank. This time it has mercury, but that's fine. You know, Euler's equation can work on water, gasoline, mercury. It can work on anything, any fluid. So we know that the height of this tank is 87 centimeters. We don't know the width of the tank. You'll notice that delta x, that dimension, is not given. So we don't know how far apart G and H are. Okay, but what we do know is we know the pressure at both of those locations. The measured pressure at G is 485 kilopascals, and the measured pressure at H is 120 kilopascals. Now wait a minute. We got to make sure that those differences in pressure kind of matches what we'd expect based on the acceleration. So look at the acceleration in the x direction. Does the pressure at G versus H make intuitive sense based on the acceleration that's given? One of the pressures is higher than the other. So it's accelerating to the right. So this A sub x says 15 meters per second to the right. So if it's accelerating to the right, what direction should the pressure be increasing? To the left. So that means that the pressure should be higher at G than H. And that is the case. All right, so far it doesn't seem to be violating anything that we've learned at this point. We don't know the pressure at F. That isn't immediately given. And in fact, that's the first thing that we need to do, is find the pressure at F. So here's the thing. Euler's equation can only go in one direction at a time when you've got acceleration in two directions. Let's say if you wanted to go from F to H, you couldn't do it in a single step if it's accelerating both in x and z. So if you want to find the pressure difference between F and H, you'd have to go from F to G, then from G to H. And when you're going from F to G, that's when you'd use the acceleration in the vertical direction. And then from G to H, you'd have to do the horizontal. Sometimes students try to get fancy and they'll like combine the acceleration in x and z. Unfortunately, that approach doesn't work. We just have to analyze the directions individually. So in this illustration, what I'd like you to do is, first of all, in step 1, find the pressure at F. Now, this is the first time that we've done a vertical acceleration before. here's Euler's equation in terms of z. And you'll notice instead of delta x, now we've got delta z. In a way, it's like we're accounting for the vertical effects twice. So the pressure plus gamma z at 2 minus the pressure plus gamma z at 1. So there's a difference in elevation there because you've got z2 and z1. And then here on the right-hand side of the equation, you're accounting for that elevation difference again. But remember on the first example how I broke the final answer up into the component of the pressure change that was due to the hydrostatic effects and the component of the pressure change that was due to this additional acceleration. That's what this is going to be doing. Is it already knows that gravity is a thing and gravity is out there and we have to account for gravity. But then there's this additional acceleration and we're accelerating downward at negative 12.5 meters per second squared. All right, so let me stop talking. I'll pause the recording here and I'd like you to first of all find the pressure at F and then see if we can find out what's the distance x. So how far apart are G and H given those pressures that we already know? Okay, in the example, it was the specific gravity that's given, so you have to use that to calculate the unit weight and the density of the fluid, because we're going to need to know both of those when we make substitutions. And now finding the pressure at F means that we're working in the vertical direction. So the acceleration we're interested in is this negative 12.5 meters per second squared. So in the vertical direction, we've got to make sure that negative sign is substituted in. And then the other thing is distinguishing 2 from 1. So 2 is F because it's above location G. Has more of the Z direction. You have to define z values. You know, you have to assume a datum someplace because we need to put in a z sub g and a z sub f. And so you could have said z sub g is 1,000 and then z sub f is 1,000.87. But just for simplicity, I said let's assume that z sub g, the bottom location, is 0 elevation, and then z sub f is 0.87 meters. And you can see the substitutions after that. And again, I've sort of grouped things together in these intermediate sums. And so there's our initial pressure of 485, and then a decrease in pressure of 115 kilopascals. And that pressure decrease is because we're going up through the fluid to get to location F. Remember, if we go back to this figure here, location F is above location G. And so ordinarily, the pressure is lower as you go up through the fluid. And this is Euler's equation already accounting for gravity and the fact that location F is higher. So there's the minus 115, and then plus 147 is because it's accelerating downward. So the downward acceleration, that pressure accumulation, is larger than the fact that it's above it in elevation. So in other words, the downward acceleration of, what was it, 12.5 meters per second squared is bigger than the g acceleration. So you don't have to separately account for g. Euler's equation already has that handled. Any questions on this first part of finding the pressure at F? All right, the distance, delta x. Let's look at that. 1.7945 meters. Oh, nope. Better. So the elevations are the same when we're in the horizontal direction. So here's the full Euler's equation, but ZH is equal to ZG, so we can just cancel out the gamma ZH and gamma ZG. That makes Euler's equation a lot simpler. The difference in pressure is equal to the negative of the distance between them, the density, and the acceleration in x. So rearranging it for delta x gives you 1.7945 meters. Any questions on that? Do I need to leave it up for a moment to, yeah? All right. Okay, so just to remind you that if you have acceleration in two directions, if you're going from one corner to the other corner, meaning that the two locations of interest have both a change in z and a change in x, you have to account for those directions in steps. So if you're going from F to H, then you first, actually it doesn't matter which step you do first. It doesn't matter if you do the horizontal first or the vertical first, but you can't go directly from F to H if there's acceleration in both the vertical and horizontal. You have to apply Euler's equation in the direction of the acceleration and find the pressure change because of that acceleration in a certain direction. All right, here's the last idea for today, and that is if the tank is open to the atmosphere, then Euler's equation can tell you the relationship between acceleration, elevation, and pressure. So before, the elevation of the liquid wasn't changing because there was a metal layer confining it from moving, and so it was just the pressure that adjusted. But let's say that we were accelerating this in the x direction. Before it was accelerated, the liquid level is going to be horizontal, and during acceleration, as that liquid sloshes to the left because of it being accelerated to the right, then we have some angle that's formed here, alpha, the angle that's formed with where the original liquid surface was. So this figure is showing both the before and the after simultaneously. Obviously, the liquid surface isn't going to be in two locations at once. But what we do is we can use Euler's equation, excuse me, and if it's accelerating to the right, then the liquid level would be higher on the left. And the pressure variation in the vertical direction is just hydrostatic. There isn't any special pressure change when we're going vertically if it's just being accelerated to the right. So one of the interesting things is that Euler's equation can be used to find the angle here, alpha. The tangent of the angle is the ratio of the acceleration in the horizontal to the gravitational acceleration. And just as an illustration of how we can use that function, that angle function, if we had a tanker truck that was 18 feet long and had a 7-foot bed depth, the question is how deeply could we fill the tank with a liquid so that it wouldn't spill if the truck is never accelerating or decelerating more than 8.02 feet per second squared. So G in the traditional units, of course, is 32.2 feet per second squared. So here we're going to say that our acceleration in the x direction is 8.02 feet per second squared, and g is 32.2 feet per second squared. So what we want to know is how much liquid could we put inside of this truck. So what is the liquid depth so that it never spills. So when it's accelerating, then if it's more full than, it's going to form some angle here, alpha. And if it was more deeply filled, then it would start to spill out. So there's some maximum depth that it can be filled. And so what I'd like you to try and attempt is find out what that angle is going to be. And then once you know the angle, how much liquid could be in there so that when it's up to the edge, it's not going to be more than 7 feet on the left side, or if it was decelerating on the right side. So the ratio of h to 9 is the same as the ratio of the acceleration horizontal to g. So in other words, if it was accelerating to the right at 9.81 meters per second squared, then it would be a 45-degree angle. But here it's accelerating not quite at the same rate as g, and so it's not going to be as long as 9. That h distance is going to be less than that. It's 2.24. And if it's going to be 2.24 meters over here on the left, then that means that the remaining component, 7 minus 2.24, is 4.76. So that's the maximum depth we can fill it at. And if it's any deeper, then it will spill when that truck is accelerating. So that's just another of the applications of Euler's equation, is to predict the liquid profile when it's in contact with the atmosphere. Okay, you've got a really good head start on Euler's equation today, and so I'd encourage you to start looking at this assignment as early as possible, Strike while the iron's hot, while it's still fresh in your mind. Get these out of the way. And I'll see you in lab today and tomorrow. I'll have the handout for you there. We're going to be doing flow visualization.